On January 15th, NASA directed its spacecraft toward 3I Atlas as the object appeared to send a final, deeply unsettling message. Subsequent data analysis revealed that the energy output and thrust produced by 3I Atlas are approximately 16 times greater than the natural limits expected for an object of its estimated size, creating a serious thermodynamic contradiction, while also being accompanied by a striking geometric improbability in which the object's trajectory and rotational axis are nearly aligned with the Sun and the ecliptic plane at a level of precision that can hardly be considered random. Against this backdrop of overlapping anomalies, physicist Michio Kaku issued a controversial warning arguing that if 3I Atlas does not fragment under the extreme physical stresses it is currently experiencing, then all purely natural explanations will collapse. This chain of uncertainty then shifts attention toward the event of March 2026, when 3I Atlas approaches the gravitational sphere of influence of Jupiter, raising the hypothesis that the object could execute a calculated orbital maneuver to leave behind an anomalous object within Jupiter's satellite system, a scenario considered impossible for natural celestial bodies due to the delta-V paradox. And after all of these continuous transformations, the remaining question is, what message Atlas is sending to us something that will be explored next? At first glance, 3 Atlas appears calm, distant and unremarkable, drifting through the inner solar system with the quiet patience of an object that does not belong to this place. Yet embedded within the soft halo of light surrounding 3 Atlas, astronomers began to notice a structure that refused to behave a narrow, coherent stream of material, extending not away from the Sun, as every known cometary model predicts, but directly toward it. To understand why this observation matters, it helps to return to the most fundamental rules governing cometary physics rules that have remained stable across centuries of observation and across thousands of individual objects. In every well-documented case, material released from a comet is shaped by two dominant forces, the pressure of sunlight itself and the continuous flow of charged particles known as the solar wind, both of which act relentlessly to push dust and gas outward away from the Sun. 3. Atlas exists within this same environment, bathed in the same radiation, immersed in the same solar wind, and subject to the same equations that have successfully described every comet observed before it. Under these conditions, any material escaping the surface of 3 Atlas should expand outward in a broad diffuse cone before being swept back, forming a tail that always points away from the Sun. Instead, what telescopes recorded was a counterflow, a structure maintaining focus and direction, while moving upstream against forces that should overwhelm it within minutes. The counterflow associated with 3I Atlas remains sharply collimated over distances approaching 400,000 kilometers a scale, comparable to the distance between Earth and the Moon, and it does so without dispersing into the surrounding vacuum. This behavior introduces an immediate anomaly, because gas produced through natural sublimation does not self-focus, does not resist external pressure, and does not preserve structure when every surrounding force is working to tear it apart. In laboratory conditions and in space-based observations alike, expanding gas clouds always spread, always thin, and always yield to dominant pressure gradients. Yet the counterflow of 3I Atlas does none of these things. One might imagine a transient outburst, a brief moment when internal stresses release material in an unusual way, but 3 Atlas offers no such simplicity. The counterflow persists across multiple observation windows, across changes in distance and geometry, and across the slow rotation of the object itself, suggesting a stable process rather than a fleeting accident. As 3 Atlas rotates, the direction to the Sun changes continuously from the object's frame of reference, and any passive jet should smear into a spiral pattern, the unmistakable signature of rotation acting on an uncontrolled release of material. Yet the counterflow of 3 Atlas remains locked in orientation, tracking the Sun with precision that implies constraint regulation and directional control. Here the emotional weight quietly enters the discussion, not as fear or excitement, but as a growing sense of discomfort born from the realization that familiar explanations no longer apply. 3I Atlas is not merely behaving strangely, it is behaving in a way that forces a pause a moment, where established intuition falters and silence fills the gap left by missing answers. This silence does not demand conclusions, but it does demand attention, because when an object like 3 Atlas violates the most basic expectations of physics without explanation, The responsible response is neither dismissal nor speculation, but careful listening. And so the counterflow of 3 at last becomes not a claim, but a question, one that quietly bridges observation to deeper inquiry as we move forward into the anatomy of energy, structure and possibility. If the counterflow of 3 at last were merely an oddity of direction, it might still be absorbed into the long history of rare but natural cometary behaviour. What elevates the phenomenon into deeper uncertainty is not only where the material travels, but how it travels, because the structure associated with 3 at last behaves less like evaporating gas and more like a deliberately shaped release. In natural sublimation, heat penetrates the surface of an icy body, unevenly causing volatile compounds to transition into gas and escape through fractures, pores, and weak points. This process produces plumes that fan outward, spreading rapidly as pressure equalizes, and no known configuration of ice and dust can force such gas into a narrow, sustained column. Yet the emission observed from 3 Atlas does exactly that, maintaining a tight geometry that resists expansion while preserving a consistent axis of motion. Measurements indicate that the width of the structure remains small relative to its length, implying confinement that natural thermodynamics cannot easily supply. To sustain such focus, material leaving the surface of 3 Atlas would need to pass through a constraining architecture, something that limits lateral expansion, while allowing forward momentum to dominate. In engineered systems, this role is played by a nozzle, a geometry designed to convert internal pressure into directed flow, but in natural cometary bodies, no equivalent structure has ever been confirmed. This discrepancy introduces a new layer of anomaly, because the physics of gas dynamics is well understood and relentlessly consistent across scales. Gas does not choose a direction. Gas follows gradients, and gas expands to fill available space, unless prevented by boundaries that 3 Atlas is not expected to possess. Some models attempt to preserve natural explanations by invoking unusual surface composition or extreme subsurface channels, yet these ideas struggle to account for the observed stability. Any channel capable of shaping flow within 3 Atlas would itself be subjected to intense thermal stress erosion and collapse, especially under continuous operation. Despite this, the emission from 3 Atlas shows no signs of weakening, widening or wandering, even as the object progresses along its trajectory and experiences changing solar input. The persistence suggests regulation rather than reaction, a distinction that feels subtle in language but profound in implication. Emotionally, this is the point where curiosity gives way to quiet unease, because the mind begins to sense a mismatch between cause and effect. 3 Atlas appears to be doing more than responding to its environment, and this perception arises not from speculation, but from the steady accumulation of incompatible details. Still, caution remains essential because history reminds us that nature often surprises before yielding to understanding. 3 Atlas does not demand that we label its behaviour, only that we acknowledge the limits of what passive processes can achieve. As this section closes, the focus shifts gently forward from how material escapes 3 Atlas to how much energy such an escape would require. The question of control naturally becomes the question of power, and in that transition the story of 3 Atlas moves deeper into the heart of physical constraint. As the discussion moves from structure to power, 3 Atlas presents a problem that is less visual but far more restrictive, because energy budgets do not bend easily, and thermodynamics leaves little room for interpretation. Every natural comet operates under a simple constraint, since the energy driving sublimation must come from absorbed sunlight, and the amount of available energy is limited by the exposed surface area of the nucleus. Observations of 3 Atlas place the diameter of the central body at approximately 5 to 6 kilometers a size, that defines the maximum area capable of intercepting solar radiation. Under standard assumptions, that surface area sets a hard upper bound on how much mass 3 Atlas can lose and how much momentum it can impart to escaping material. When researchers calculated the energy required to sustain the observed counterflow associated with 3 Atlas, the numbers refused to align with this constraint. The brightness, persistence, and velocity of the emitted material imply an energy output equivalent to what would normally require a surface area roughly 16 times larger than what 3 Atlas appears to possess. This discrepancy is not subtle, and it does not live in the margins of uncertainty, where measurement error might quietly resolve the conflict. Even generous assumptions about albedo composition and heat retention fail to close the gap between what 3 Atlas can absorb from the sun and what the emissions demand. In natural systems, such an imbalance usually resolves itself through rapid fragmentation, because a small body subjected to excessive internal stress tends to break apart, exposing more surface area and relieving pressure. Yet, 3 at last shows no clear evidence of catastrophic cracking or progressive disintegration, even as the energetic output continues over extended periods. At this point, 2 broad explanatory paths emerge, each carrying different implications for how we understand 3I at last. The first path suggests that existing thermal models are incomplete, and that under rare conditions, cometary material may channel solar energy far more efficiently than currently believed. This possibility remains scientifically valid, though it requires revisiting assumptions that have held across thousands of observations and decades of modelling. The second path proposes that the energy driving the emissions of 3 Atlas does not originate solely from absorbed sunlight, but from an internal source capable of supplementing or replacing external heating. Here the tone naturally shifts not toward alarm but toward a quieter form of tension, because internal energy sources in small interstellar bodies are not easily justified without invoking unfamiliar mechanisms. 3I Atlas does not display the chaotic variability one would expect from unstable internal reactions, and instead maintains output levels that appear regulated rather than erratic. Emotion enters gently through restraint, as the realization settles that neither explanation resolves the problem cleanly without introducing new questions. 3 Atlas occupies a narrow space where natural physics feels stretched, yet definitive alternatives remain just beyond confirmation. This section does not ask for belief, and it does not argue for conclusions, because the role of energy accounting is simply to define boundaries. What 3I at last accomplishes through its emissions appears to exceed those boundaries, and the significance lies in recognizing that excess rather than rushing to name it. As the narrative moves forward, the focus transitions away from how much power 3 Atlas uses and toward how precisely its motion unfolds through space. Energy alone raises doubts, but geometry and probability will soon add structure to those doubts, guiding the inquiry into the architecture of 3 Atlas's path. When scientists speak of randomness in space, they are usually referring to orientation, because objects that drift between stars carry the chaotic legacy of countless past interactions. 3 Atlas derive from interstellar space with no known gravitational ancestry within the solar system, which means that under ordinary assumptions, the orientation of 3I Atlas should reflect that chaos rather than any preferred alignment. Yet measurements of 3 Atlas reveal a configuration that immediately stands apart, because the rotational axis of 3 Atlas is aligned toward the Sun within a margin of roughly 7 degrees. Such alignment would be unremarkable if 3 Atlas had formed within the solar system, where long-term gravitational and thermal interactions can gradually sculpt orientation. 3 Atlas, however, is a visitor, and visitors do not have time to be reshaped so precisely. The gravitational influence of the Sun during a brief flyby is far too weak to reorient the spin of 3I Atlas in any significant way, which means that the alignment observed today is almost certainly the alignment with which 3I Atlas arrived. From a statistical perspective, this is where probability begins to matter. For a randomly oriented object in 3-dimensional space, the chance that its rotational pole would naturally align this closely with the Sun is small, but still within the realm of coincidence when considered alone. What complicates the picture is that this alignment does not exist in isolation. 3I Atlas also travels along a trajectory that lies unusually close to the ecliptic plane, the flattened disk in which the planets orbit, and where most of the solar system's mass and dynamical activity are concentrated. Interstellar objects are not expected to respect this geometry. They can arrive from any direction at any inclination, and previous visitors entered the solar system on steep paths that slice through the planetary plane before continuing outward. 3I Atlas behaves differently, sliding along the same broad corridor occupied by the planets themselves, and when this orbital alignment is combined with the polar alignment, the statistical picture changes dramatically. The joint probability of both conditions occurring by chance drops to roughly 1 in 10,000, a figure that remains approximate but illustrative of the scale involved. In scientific terms, a 1 in 10,000 event does not automatically imply design or intent. Rare events do occur, and nature is capable of producing outcomes that feel astonishing when viewed in isolation. However, probability gains meaning when it accumulates, and 3I Atlas is already associated with multiple independent anomalies. The alignment of 3I Atlas does not explain the counterflow, and the counterflow does not explain the energy imbalance, yet each anomaly adds weight to the same central question. Emotionally, this stage of analysis does not provoke fear, but rather a subtle cognitive tension, the feeling that assumptions once taken for granted may no longer be sufficient. 3. Atlas invites this tension by occupying a narrow statistical corridor, one that exists but is seldom travelled. Some researchers argue that chance alone can still account for the orientation of 3i Atlas, and this position remains defensible within strict statistical logic. Others note that when improbable geometry aligns with sustained physical anomalies, the underlying assumption of randomness deserves closer examination. 3. Atlas does not force a verdict, but it does challenge complacency, because probability is not merely about numbers, it is about context. In the context of 3 Atlas, alignment becomes more than an abstract calculation, and instead becomes a bridge between geometry and intention, whether natural or otherwise. As this section draws to a close, the narrative shifts gently forward. The orientation of 3 Atlas sets the stage, but it is the destination of that orientation, particularly the encounter awaiting near Jupiter, that will further test whether chance alone can bear the explanatory weight. Once orientation and probability are considered together, the path of 3 Atlas begins to feel less like a simple passage and more like a carefully maintained trajectory. 3 Atlas is not merely crossing the solar system, but approaching a region where gravity becomes layered and complex, and where small changes in motion can lead to vastly different outcomes. As 3 Atlas advances inward, its projected path carries it toward the gravitational domain of Jupiter, the most massive planet in the solar system and a dominant sculptor of orbital dynamics. Jupiter's influence extends far beyond its visible atmosphere, creating a vast sphere where trajectories can be bent, accelerated, or subtly reshaped. Under ordinary circumstances, an interstellar visitor like 3 Atlas would pass through this region quickly, its high velocity allowing little time for meaningful interaction. 3. Atlas, however, approaches Jupiter along a geometry that maximizes exposure, traveling close to the ecliptic plane and arriving at a time when the relative positions of the Sun and planets align favorably. This configuration invites a hypothesis that must be handled with care, because it rests not on intent but on possibility. If the sunward counterflow observed from 3i Atlas functions as more than a passive emission, then it could serve as a mechanism for fine adjustments, small corrections applied gradually over long distances. Such corrections would not need to be dramatic. In celestial mechanics, minute changes applied early can accumulate into substantial differences later, especially when gravity amplifies their effects. 3 Atlas displays a stability that supports this line of reasoning. The consistent orientation of the counterflow, the persistence of its alignment with the Sun, and the absence of chaotic drift suggest that 3i Atlas maintains control over its attitude, rather than surrendering it to rotation alone. From this perspective, the encounter with Jupiter becomes more than a coincidence of timing. The path of 3 Atlas appears tuned to pass near the threshold, where Jupiter's gravity begins to rival that of the Sun, a region known for its sensitivity to perturbation. Emotion enters quietly here, not as excitement, but as a sense of anticipation tempered by restraint. 3. Atlas seems to be approaching a decision point in space, a place where trajectories can change character without violence or spectacle. Natural explanations remain available, and it is possible that 3 Atlas simply occupies a rare but permissible corridor through the gravitational landscape. Yet the consistency required to maintain such a corridor, especially in combination with earlier anomalies, strains the idea that 3 Atlas is merely reacting to chance encounters. If the counterflow of 3 Atlas functions as a course-correcting influence, then the long arc toward Jupiter could represent a calculated approach rather than an accidental drift. This does not require advanced assumptions, only acknowledgement that controlled thrust, even at modest levels, can shape destiny over astronomical distances. 3 Atlas does not announce its purpose, and the hypothesis of calculation remains provisional. What matters is that the geometry allows such a hypothesis to exist without violating known physics, provided the emissions of 3 Atlas are not purely passive. As this section settles, the focus turns toward what such a calculated approach would demand in terms of energy and momentum. The quiet elegance of 3 Atlas's path leads naturally to a harder question, because approaching Jupiter is one thing, but changing velocity enough to remain there is something entirely different. As the trajectory of 3 Atlas carries it toward Jupiter's gravitational domain, The discussion shifts from geometry to momentum, because motion in space is ultimately governed by velocity rather than intention. 3 Atlas is travelling through the solar system at an extraordinary relative speed, one that reflects its interstellar origin and far exceeds the velocities of objects native to the planetary neighbourhood. For 3 Atlas, this speed is not a subtle detail, but a defining constraint. At the distance where 3 Atlas will pass near Jupiter's gravitational boundary, the maximum velocity an object can have and still be captured into orbit is only a few kilometers per second. Calculations show that 3 Atlas exceeds this threshold by more than 60 kilometers per second, creating a gap that cannot be ignored or minimized through rounding or uncertainty. This difference, known as the delta V problem, represents the amount of velocity that would need to be removed for any portion of 3 Atlas to remain gravitationally bound to Jupiter. In natural fragmentation events, when comets split or shed material, the velocities involved are modest. Fragments drift apart at speeds measured in meters per second, or in extreme cases a few kilometers per second, values consistent with explosive sublimation and internal stress release. 3 Atlas operates in a completely different regime. To cancel more than 60 kilometers per second of approach velocity, any departing fragment would require an impulse comparable to those produced by high-energy propulsion systems rather than natural outgassing. This is where the paradox sharpens, because kinetic energy scales with the square of velocity, meaning that the energy required to slow such a fragment increases dramatically as speed rises. For 3 Psi Atlas, the energy needed to achieve capture near Jupiter approaches levels that natural chemical or thermal processes cannot supply without destroying the material involved. If 3 Atlas were to shed mass naturally during its passage, the fragments would continue forward, slightly altered, but fundamentally unbound. There is no known mechanism by which a passive object like 3 Atlas could abruptly redirect that much momentum in a precise and localized way. The emotional tone here remains controlled, because this is not a claim but a boundary. 3 Atlas either remains intact and passes on, or something fundamentally different occurs that demands explanation beyond fragmentation physics. In scientific language, the appearance of a new Jovian satellite after the passage of 3 Atlas would constitute what researchers call a technological signature. This term does not imply origin, intent, or intelligence directly, but simply describes an outcome that natural processes cannot reproduce under known laws. 3 Atlas does not need to reveal structure or transmit signals for such a signature to exist. The signature would be encoded in motion itself in a change of velocity that exceeds what nature can provide without assistance. Still, restraint is essential because absence of evidence remains a possible outcome. 3 Atlas may pass through Jupiter's domain without leaving anything behind, in which case the delta V paradox remains theoretical rather than observational. Yet the paradox matters precisely because it defines a clear test. 3 Atlas sets up a scenario where the universe will either behave as expected or quietly demonstrate that an additional mechanism is at work. As this section concludes, the narrative settles into a waiting posture. 3 Atlas continues along its path, carrying with it a question written not in speculation but in numbers, and the answer will depend not on belief but on what remains when the motion is complete. As 3 Atlas continued its journey inward, observers began to register a structure so large that it challenged intuition before it challenged theory. Extending behind 3 Atlas was an immense anti-tail, a luminous formation stretching millions of kilometers through space, while maintaining a coherence that felt incompatible with fragility. In conventional cometary, behavior tails are ephemeral expressions of loss shaped quickly by radiation pressure and solar wind, and dispersed almost as soon as they form. 3 Atlas departs from this pattern because the anti-tail associated with Atlas persists, grows, and remains visually distinct across observation periods that span weeks and months. The sheer scale of this structure introduces the first layer of anomaly, because length alone implies sustained mass loss over time rather than a brief eruptive event. For 3I Atlas to generate an anti-tail approaching 3 million kilometers material must be continuously supplied, replenished at a rate that remains stable rather than diminishing as surface volatiles deplete. This raises a fundamental physical concern. Small bodies like 3 Atlas are not expected to sustain prolonged mass loss without catastrophic consequences because internal cohesion decreases rapidly as material escapes. In natural scenarios, such stress manifests visibly. Cracks widen, fragments separate, and brightness fluctuates as the nucleus breaks apart and exposes fresh surfaces. 3I Atlas shows none of these symptoms in a decisive way. Despite the magnitude of the anti-tail, Atlas maintains a compact nucleus, whose brightness variations suggest rotation, not disintegration. This disconnect between output and integrity forms the core anomaly. 3 Atlas appears to be shedding enormous quantities of material while preserving a stable structure, a balance that contradicts expectations rooted in thermomechanical modelling. One might argue that projection effects exaggerate the perceived scale of the anti-tail, but this explanation weakens under multi-angle observation. Data collected over time confirm that the anti-tail of 3 Atlas is not a transient illusion, but a persistent physical feature aligned with the object's trajectory and illumination geometry. Emotion enters here as a quiet tension rather than alarm. There is something unsettling about watching 3 Atlas lose so much while remaining whole, because the mind expects visible consequences that never quite arrive. This tension deepens when energy considerations return to the foreground. To sustain an anti-tail of this magnitude, 3 Atlas must either access a vast reservoir of volatile material or employ a mechanism that converts energy into directed mass loss with unusual efficiency. Neither option resolves easily. Volatile reservoirs are finite, and efficiency gains are bounded by physics that has proven remarkably consistent across comet populations. The anti-tail of 3 Atlas therefore occupies a conceptual gap. It is too large to be ignored, too persistent to be dismissed, and too orderly to be comfortably explained by chaotic erosion alone. As this section draws to a close, the anti-tail becomes more than a structure. For 3I Atlas, the anti-tail functions as a signature of imbalance, a visible record of processes operating beneath the surface that remain only partially understood. This imbalance does not yet demand reinterpretation of origin, but it does demand continuity of inquiry. 3. Atlas carries its anti-tail forward like a question written in light, inviting deeper examination of what must occur when loss does not lead to collapse. In the language of classical cometary physics, prolonged stress leads inevitably to fragmentation, because small bodies cannot shed mass indefinitely without compromising their internal cohesion. 3. Atlas occupies precisely the regime where such failure should be unavoidable, since the sustained mass loss implied by the anti-tail would normally weaken structural bonds beyond recovery. Models built on decades of observation predict a clear sequence. As thermal gradients intensify and volatile pockets empty, fissures propagate, rotational stresses amplify, and the nucleus of an active comet begins to separate into discrete fragments. 3I Atlas has been watched carefully for each of these warning signs. Astronomers have monitored brightness curves, searched for sudden changes in morphology, and tracked subtle deviations in motion that would signal structural breakup. What they found instead was continuity. 3 Atlas remains stubbornly intact, rotating, emitting, and progressing along its trajectory without the chaotic signatures associated with disintegration. This persistence introduces a contradiction that is difficult to reconcile. 3 Atlas behaves as though it is losing mass at rates that should exceed structural tolerance, yet it does not respond in the way natural bodies historically have. One might suggest that 3 Atlas is unusually strong, perhaps composed of materials denser or more cohesive than those found in typical comets. However, such strength would need to exceed known bounds by a significant margin, and it would need to remain uniform across the entire body to prevent localized failure. 3. Atlas offers no direct evidence for such extraordinary composition. Spectral data remain broadly consistent with icy dust-rich material rather than exotic structural matter. This leaves scientists facing an uncomfortable mismatch between expectation and observation. 3. Atlas appears to occupy a state that models describe as unstable, yet it persists as though governed by different rules. The contradiction becomes sharper when time is considered. Fragmentation is not merely a function of intensity but of duration, and 3 Atlas has sustained its activity long enough that cumulative damage should already be apparent. Instead, the surface behavior of 3 Atlas suggests regulation rather than exhaustion. Emissions do not spike chaotically, nor do they collapse abruptly, but maintain a consistency that implies balance. Emotion enters the narrative quietly at this stage. There is a subtle unease in watching a prediction fail repeatedly, not because failure is frightening, but because it undermines confidence in familiar patterns. 3. Atlas does not violate equations openly. 3. Atlas simply refuses to follow the expected outcome when those equations are applied in sequence. This is why the prediction of fragmentation has become a focal point rather than a conclusion. 3 at last sets up a test that is temporal rather than theoretical one that resolves only as time passes and stress accumulates. If 3 at last were to fragment abruptly, the contradiction would dissolve, and the anomalies observed so far would fold back into the category of extreme but natural behaviour. If 3I at last remains whole, the contradiction deepens because the physical cost of stability would require an explanation beyond passive response. At this stage, no declaration is warranted. 3I at last continues forward, carrying both prediction and contradiction in parallel, forcing observers to wait rather than decide. The significance of this waiting lies not in suspense, but in discipline. 3. IATLAST reminds the scientific process that reality has priority over expectation, and that some answers arrive only when the universe has finished unfolding the conditions of its own experiment. When scientists search for context to understand 3. At last, they inevitably return to the first confirmed interstellar visitor Oumuamua because precedent provides the only available framework for comparison. Oumuamua entered the solar system unexpectedly, departed rapidly, and left behind a trail of unanswered questions that remain unresolved years later. Like 3 at last, Oumuamua exhibited non-gravitational acceleration that could not be fully explained by conventional outgassing models. In the case of Oumuamua, no visible cometary tail accompanied this acceleration, forcing researchers to propose exotic explanations such as hydrogen, ice, nitrogen ice, or radiation pressure acting on an unusually thin structure. 3 Atlas echoes this earlier mystery while simultaneously amplifying it, where Oumuamua accelerated without a visible tail. 3 Atlas accelerates while producing emissions that appear too structured and too energetic for its estimated size. The comparison matters because Oumuamua taught the scientific community a difficult lesson about premature certainty. Early assumptions about Oumuamua were revised repeatedly as new data exposed gaps in existing models, and no single explanation has yet achieved broad consensus. 3 Atlas arrives in the shadow of that uncertainty. Researchers approach Atlas with greater caution, aware that dismissing anomalies too quickly risks repeating the same analytical blind spots. At the same time, 3 Atlas differs in crucial ways that limit direct analogy. 3 Atlas remains observable for an extended period, allowing repeated measurements rather than fleeting glimpses. This persistence transforms 3 Atlas into a more rigorous test case. Where Oumuamua passed before hypotheses could be fully stress-tested, 3 Atlas lingers long enough for predictions to confront observation. The similarities between Oumuamua and 3 Atlas raise a deeper question about classification. If both objects share non-gravitational acceleration, yet display different physical signatures, then interstellar visitors may represent a broader category than previously assumed. One possibility is that 3 Atlas and Oumuamua belong to a natural population of objects shaped by processes unfamiliar to solar system science. Another possibility is that both objects occupy the boundary between natural debris and something more structured, though such interpretations remain speculative by necessity. Emotion surfaces here as reflection rather than tension. 3. Atlas invites reconsideration of how precedent shapes expectation, reminding observers that first encounters rarely define final understanding. The lesson of Oumuamua is not that extraordinary explanations are required, but that incomplete data can masquerade as certainty. 3 Atlas benefits from this lesson by being observed with more patience and less urgency to conclude. Yet comparison also sharpens contrast. 3 Atlas presents anomalies that are not merely subtle deviations, but layered inconsistencies that persist across multiple domains of physics. Where Oumuamua hinted at unknown processes, 3 Atlas sustains them. This endurance makes Atlas harder to dismiss as a statistical outlier or a singular curiosity. The comparison does not resolve the nature of 3 Atlas. Instead, it reframes the question by placing Atlas within an emerging pattern, rather than treating it as an isolated puzzle. As this section closes, Oumuamua recedes into the background not as an answer, but as a reminder. 3. Atlas stands on its own trajectory, informed by precedent yet defined by its own behaviour, continuing forward as a case study in how the universe occasionally presents questions that refuse to be hurried. Science advances by building frameworks that explain patterns, and for long stretches of time those frameworks feel stable, reliable, and complete. 3. Atlas now stands at a point where several of those long-standing structures begin to strain under their own weight. For generations, cometary science has relied on a coherent set of assumptions. Small icy bodies respond passively to solar heating release material through sublimation fragment under sustained stress, and follow trajectories shaped primarily by gravity. 3 Atlas has engaged with each of these assumptions and quietly failed to conform. The emissions of 3 Atlas resist passive explanations, the energy output of 3 Atlas exceeds surface area limits, and the structural integrity of 3 Atlas persists where fragmentation is expected. Individually, each discrepancy might be absorbed as an exception. Together they form a pattern that challenges the completeness of the existing system rather than any single parameter within it. Frameworks do not collapse all at once. They weaken gradually at first, accommodating anomalies through patches and adjustments, then accumulating inconsistencies that demand more radical revision. 3 Atlas accelerates this process because the inconsistencies associated with Atlas are not confined to one domain. They span thermodynamics, gas dynamics, structural mechanics, orbital geometry, and probability, creating tension across the entire explanatory network. At this stage, the scientific response is not abandonment but reassessment. 3 Atlas forces researchers to ask whether the current framework describes all small interstellar bodies or only those formed and evolved within familiar environments. One possibility is that 3 Atlas represents an extreme end of a natural spectrum that has not yet been sampled. If so, the collapse is not of physics itself, but of assumptions about uniformity and prevalence. Another possibility is that 3 Atlas operates under constraints that existing models were never designed to accommodate. In this case, the collapse is more fundamental because it suggests that some observed behaviours do not emerge from passive interaction with sunlight and gravity alone. Emotion enters here as intellectual humility rather than alarm. There is a quiet recognition that frameworks are tools, not truths, and that 3 Atlas is revealing the limits of those tools. 3 Atlas does not accuse science of failure. 3 Atlas simply occupies a region of possibility that science has not fully mapped. The discomfort arises from familiarity. The models challenged by 3 Atlas have served well for decades, and letting go of them, even partially, feels like stepping into uncertainty without a guide. Yet this moment is not unprecedented. History shows that progress often begins when data accumulates faster than explanation, and 3 Atlas has become such a data point. The collapse described here is therefore not destruction, but transition. 3 Atlas signals the moment when refinement is no longer sufficient and re-examination becomes necessary. As this section settles, the narrative does not rush to replace old frameworks with new ones. Instead, 3 Atlas invites patience because understanding often emerges not from immediate reconstruction, but from allowing uncertainty to remain visible. In that visibility, science regains its strength. As 3 Atlas approaches the outer regions of the solar system, attention shifts from interpretation to observation, because some questions can only be answered by instruments already waiting in silence. Among those instruments, the Juno spacecraft occupies a unique position, circling Jupiter and continuously reading the invisible dynamics of space around the giant planet. Juno was not designed to study interstellar visitors, yet Juno is exquisitely sensitive to disturbances in plasma magnetic fields and energetic particles. If 3 Atlas interacts with Jupiter's environment in any unusual way, Juno is positioned to notice the consequences rather than the cause. The space surrounding Jupiter is not empty. It is filled with a vast magnetosphere, a rotating ocean of charged particles shaped by Jupiter's powerful magnetic field. Any significant release of energy near this region leaves traces. Plasma heat waves propagate, and magnetic lines flex in response to sudden injections of momentum or charged material. If 3 Atlas were to undergo a high-energy event during its passage even far from Jupiter's visible atmosphere, the surrounding plasma would not remain silent. Juno's instruments continuously record fluctuations that would allow scientists to distinguish between routine background noise and something more abrupt. In natural scenarios, cometary interactions with planetary magnetospheres are gentle. Material disperses, gradually producing subtle, diffuse signatures that fade quickly into the background. The scenario involving 3 Atlas carries a different implication. If the emissions associated with Atlas include any form of concentrated energy release, the resulting disturbance would stand out against Jupiter's otherwise predictable plasma environment. 3 Atlas does not need to approach Jupiter closely for such effects to occur. Even interactions near the boundary of Jupiter's gravitational influence could couple with magnetic structures extending millions of kilometers into space. Emotionally, this stage of the narrative is defined by restraint. There is no anticipation of spectacle, only the quiet expectation that data may arrive without announcement. Juno does not interpret. Juno records, and in doing so, Juno transforms speculation into something measurable. For 3I at last, this means that certain hypotheses move from abstract discussion into the realm of empirical testing. If no unusual plasma signatures appear, many speculative paths will quietly close. If, however, Juno detects disturbances inconsistent with passive material release, the implications would extend beyond 3I at last itself. Such data would suggest that the interaction involved directed energy rather than diffuse loss. 3I at last would not be identified by shape or composition in that moment, but by effect. The universe would be speaking through response rather than revelation. It is important to note that absence of evidence remains a meaningful outcome. If Juno records nothing beyond ordinary fluctuations, 3 Atlas can still be understood as an extreme but natural object. This balance is essential to the scientific posture surrounding Atlas. The role of Juno is not to confirm extraordinary ideas, but to ensure that extraordinary claims remain accountable to observation. As this section draws to a close, 3I Atlas continues toward its encounter, and Juno continues to listen. Between them lies a region of space where motion energy and magnetism intersect, and where the difference between natural behavior and something else may quietly reveal itself. As the observations of 3 at last approach their natural pause, the discussion shifts away from mechanisms and measurements, and toward meaning not as conclusion but as context. 3 Atlas has not delivered an answer, but 3 at last has delivered a moment-to-moment, where familiar categories feel insufficient without yet being replaced. In science, moments like this are rare and easily misunderstood. 3 Atlas does not announce a revelation, and Atlas does not demand belief, yet the accumulation of unresolved behavior forces a reassessment of how knowledge is organized. If 3 at last ultimately resolves into a natural explanation, then 3 at last will expand the boundaries of what nature is capable of producing between stars. Such an outcome would require revisions to country physics, interstellar formation models, and assumptions about energy balance, but it would remain within the long tradition of nature surprising expectation. If 3 at last does not resolve cleanly, then the implication is not immediately extraordinary, but quietly profound. 3 at last would represent data that does not fit within existing shelves of explanation, suggesting that the catalogue itself may be incomplete. This is where the metaphor of a cosmic library becomes useful, not as poetry, but as structure. Human knowledge occupies only a few shelves filled with volumes written from local experience and limited encounters. 3 at last may be nothing more than an unfamiliar book placed among familiar titles. Alternatively, 3 at last may be the first page of a section humanity has not yet learned how to read. Emotion here is deliberately restrained because awe is most stable when it's quiet. 3 Atlas does not inspire urgency, but contemplation. The slow realization that the universe may contain archives written long before observers were present,